Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about linear momentum in the context of Newton's laws of forces. We begin as always with a brief review of the territory that we have so far covered, the ground we've so far covered. The main things to recall are that I have defined for you linear momentum for an object, that it is the object's mass times its velocity. And maybe also, what do Newton's laws say? You can also recall that Newton's first law says that an object at rest will stay at rest, and an object in motion remains in motion with constant velocity if the net force on the object is zero. Newton's second law, of course, is the one that says that the sum of forces is mass times acceleration, and Newton's third law is the one that says that F12 is equal to negative F21. That is, if you have two objects which are interacting with each other, then the force of the first object on the second object is equal to the force of the second object applied to the first object. So these are the things that we need to recall in order to basically do today's lecture. So the first one to note is that the first and second law, these two laws right here, both govern not so much velocity as momentum. So these govern changes in momentum or linear momentum. In governing changes to linear momentum, this statement actually becomes, if the sum of forces on an object is zero, then the impulse is actually zero for that object, or in other words, the change in momentum is zero for the object. This law right here similarly can be changed from F equals ma to say that the force acting on an object is the change of an object's momentum per unit time. And so what that's actually equal to is m times a, this would be delta v over delta t, plus rate change of the object's mass times time, and times velocity, excuse me. And we might note again that this term right here, this acceleration term, is actually a delta v over delta t. Now, for most objects that we've dealt with so far, the mass is assumed to be constant while interacting with everything else. But for some objects, the mass may be decreasing or increasing. For example, if you have a space rocket or a rocket in general, it propels its fuel as exhaust, and that expulsion of the fuel propels the rocket. So the mass is in fact changing in that interaction. So now we should consider this third law a little bit more. So the first two are basically telling us that forces change linear momentum. And so if there's an unbalanced force acting on an object in a system, then that object's linear momentum will change, and if there is no such unbalanced force, then the object's linear momentum does not change. This third law is interesting because while the first two govern changes in linear momentum for an object, the third law governs interactions between pairs of objects. So this governs interactions with a pair or between a pair of objects. And we could actually just say between differing objects or different objects. And the reason why that is important is because a system in general consists of, well, the objects within that system and any interactions going on between those objects. So if I have two objects, let's say I have object 1 and I have object 2, and they're going to have an interaction of some sort between them, then the force that object 1 applies to object 2 and the force that object 2 applies back to object 1 must be equal. So the force from object 1 acting on object 2, 1 acting on 2, must be equal to the force of 2 acting on 1. That's object 2 interacting with object 1. And if we include direction, then they're in the opposite directions. So this one right here might have a force in this direction, for example. That would be the force of object 1 acting on object 2. And this one right here would have, therefore, another force of object 2 acting on object 1, which is in the opposite direction but equal of magnitude. Now, if I was going to plot forces and time, so maybe I have a little plot, and on this axis I have force, and on this axis I have time. And I say I want to plot the interaction between object 1 and 2, maybe in a collision, for example, where they crash into each other. Or maybe it's they're repelling each other because they are charged objects, which we get into in physics 2 a bit more. Whatever it is, maybe the force between them looks like this. Okay, so maybe this is the shape of the force as a function of time. And maybe now, so this could be force of object 1 acting on object 2. Maybe we also draw the force of object 2 acting on object 1. Well, that will have to look like this. This is force F21. It's in the opposite direction, but it's of equal magnitude. And that means that if this one curves upwards and we call positive, then this one would curve downwards and would be negative. Okay? And notice that that's true at any time. So this right here and this right here should be equal to each other. If I pick a different time, this force here and this force here are equal to each other, and so on, at least within the limits of the drawing that I've made by hand. Well, if that's the case, then that means if I want to figure out changes of momentum, going back over here, I have a pair of objects which are interacting, and the force is equal to the rate change of momentum times time. It follows from that if I have area under sum of forces, or net force, whatever you want to call it, sum of forces, which is equal to net force, versus time, then I get change in momentum. So this area is equal to change in momentum, or in other words, it is equal to impulse. And so we could say impulse J. All right, and this again comes from this sum of forces is equal to rate change of linear momentum. Okay, this is just another way of rearranging this equation so that change in momentum is isolated. So we come back down here and we notice that for all time, these two have equal values to each other and opposite sides. That means that for any period of time that we'd like, including the period that is for the entire interaction, these two areas are equal. So this area and this area are equal areas. What does equal areas mean? Well, that means that the object 1 has the same magnitude of change in momentum as object 2. So equal areas, let's actually just copy this little section of it over. Whoops, not very good copying. There we go. Equal areas in this context means that we have equal impulses or equal changes in momentum. Okay, and this is for any pair of interacting objects. Now again, remember that a system of objects consists of basically all the objects and their interactions. But every object in the system is interacting with each other object in the system, one-on-one. That means that for any force that is being applied to one object in a system, an equal force in the opposite direction is being applied to some other object in the system. Okay? So that in turn means that momentum changes, delta P for object 1 plus delta P for object 2 plus delta P for object 3 plus, and so on until we've got all the objects, must add to 0. That's the real significance of Newton's laws taken as a set of 3 laws. We have Newton's first law, Newton's second law, Newton's third law, taken all 3 together, and this is why it's important that we put the 3 together. Taken all 3 together, the implication is that within a closed system, so a system for which there are no outside forces, the total linear momentum of the system should be conserved. So Newton's laws imply conservation of linear momentum. This points in some sense to a thing called Noether's theorem or Noether's theorem. I'm not really sure the pronunciation of the name, which basically says that symmetries in physics tend to imply conservation laws. So we have this lady to thank for that idea. What's the symmetry here? Well, the symmetry basically is that if a force is being applied to one object, then that same force must be applied to some other object somewhere. There's a sort of symmetry here, and that in turn implies conservation of linear momentum. So this is an example, although it was discovered before Noether's theorem. This was an example of this theorem working out in physics. So maybe a brief example, although I'm not going to do a momentum conservation per se example. So suppose that we have a bullet which is shot into a ballistic jelly, and the bullet is initially traveling at 360 meters per second to the right, and it has a 15 Newton force to the left from the ballistic jelly. We want to know after how much time does the bullet come to a stop. So this is assumed to be constant and initially applied at time 0. We therefore use that the net force is the rate change of the linear momentum, and so that means that the time to bring this bullet to a stop must be the linear momentum change divided by the net force. So this in turn is m delta v over net force. And so plugging in, we get a total time of about 0.72 seconds. That's all for today. Thanks for watching.